So,
Your mic is not working for sure, so.
so the important mic is the one that Gergo has. So please, Gergo, ahead.
Thank you very much for the kind introduction. A big thanks goes to Anna and Giorgio for the organization. It's really a pleasure for me to be here and tell you about our research here in Brazil and to have the possibility to discuss with all of you. So the talk is going to be about anomalous transport on the lattice, continuing the theme that was started in the previous session about the chiral magnetic effect. We have seen experimental results, we have seen the fundament for the theory, and here I would like to give you a little bit more details and insight about how one can calculate conductivities on the lattice from the first principles. This is work done in collaboration with my colleagues from Budapest, where I am affiliated since the beginning of this year, Eduardo Garnacho and Gergely Marco, and also colleagues from Bielefeld, where I used to be, Bastian Brandt and Dean Valois. So, an appetizer, what is going to come is I will present you the first fully non-perturbative determination of in-equilibrium anomalous transport coefficients, the chiral separation effect, and a local chiral magnetic effect. So, basically, Dima already told us that in equilibrium, it's a triviality that the chiral magnetic effect, the global chiral magnetic effect, vanishes, and that this is an out of equilibrium effect. And nevertheless, there are surprising findings every now and then in the literature which predict a non-zero result in equilibrium. So one of the aims of this talk is to clarify how these results can be cured and how we can really see that in equilibrium, global chiral magnetic effect currents should vanish. So, in order to get there, I will introduce very briefly the topic, and then I will walk you through the inequilibrium CME, the inequilibrium CSE, and the local inequilibrium CME, which we propose here. So before that, just a very brief overview that Lattice QCD is actually the optimal tool to learn about these kind of things, because we can simulate directly from first principles the strong interactions on the lattice. There are many groups all around the world who do work on this, and a lot of effort has been going into this to find the phase diagram, the equation of state, fluctuations, transport phenomena, and now also anomalous transport phenomena. Let me point you to the recent review that I wrote last year, which summarizes these efforts. So, anomalous transport is as opposed to usual transport, where you have a vector current due to an electric field by means of some conductivity. The chiral magnetic effect is an anomalous transport where you have a vector current due to a magnetic field. Due to CP quantum numbers, you can find out that this corresponding chiral magnetic effect conductivity is a CP odd quantity. And then let me also introduce the chiral separation effect, where you have an axial current due to the magnetic field. In this case, you have a CP even CSE conductivity. We are after these conductivities here. As we have heard, this can be found in condensed matter systems. There is an ample and very intense experimental search for these quantities, because it would provide us an indirect way to probe topological fluctuations in QCD matter in a heavy ion collision. So that would be really, really interesting to see it. And let me also show a couple of recent reviews, especially the one by Fu Chang is very interestingly showing us the problems that are related to the background in the heavy ion collision setup, for example. And there he is. So this is the hand-waving argument, which I think all of you have seen at least once, maybe, but it is already shown today, so I'm just very briefly mentioning that if you consider billiard balls, quarks as billiard balls that have some spin and momentum, and you switch on a magnetic field which aligns their magnetic moment, so their spins, and you also assume that there are more right-handed than left-handed quarks in the system, then you end up with an electric current which moves in the direction of the magnetic field. And there is a very similar effect, the chiral separation effect, where you play the same game, just instead of a chiral imbalance, you have to impose an imbalance between matter and antimatter. So more quarks than antiquarks, for example, and then you end up with an axial current in the final state on the right hand side. So this is the hand waving picture, which gives us an intuition of what we are looking for, but this is not the full thing. There are several issues or several caveats that we have to keep in mind here, and those are the following. QCD, the theory that I'm going to consider here, is a quantum field theory, which requires renormalization and regularization in the ultraviolet. The previous picture obviously didn't say anything about that. The previous picture implicitly assumed that we have massless fermions because we assume that we can talk about right and left-handed quarks and they don't change into each other, for example. But in reality, we have massive fermions in QCD, so that can be an effect. Obviously, quarks are not billiard balls, but they interact also strongly with each other and not just with the magnetic field. That's an effect that we can consider in lattice QCD simulations completely and systematically. And one more point that I would like to, in particular, emphasize here is the inequilibrium and out of equilibrium nature. The previous plot didn't say anything about whether this is a current that is generated that will flow forever and will stay there in equilibrium, or is it just an out of equilibrium response that is there in the very first moments when you kick the system with such external conditions as the magnetic field and the chiral imbalance. So let me first of all consider this inequilibrium versus out of equilibrium difference. And in order to highlight and introduce to you what I mean by that, let me consider another example, an easier example, a standard one, electric charge transport due to an electric field. Imagine that you have a box in which you have some plasma and you have an electric field that you switch on in this box, and what is going to happen to the plasma? First of all, so here you can see these orange arrows represent the electric field. This points towards the right, and then you have a plasma, so there are charge carriers in it. The charge carriers experience the Lorentz force, right? The electric field tries to accelerate them. So there is an initial current that goes on. This is an out of equilibrium response. And then after you wait a while, you will see that these charges start to accumulate. Positive charges will accumulate on the right-hand side of your box and negative charges on the left-hand side of your box. And then the current goes on and on. Does it go on forever? Not really. After a while, you reach an equilibrium charge distribution. And this is the equilibrium, unambiguously defined by the equilibrium conditions, because there are no currents flowing anymore, but the charge profile is fixed. The charge profile will look something like this, which is actually defined by the fact that in this case, electric forces and pressure gradients or diffusion forces cancel each other exactly. So what does this tell us? It tells us that there were two different kinds of responses in this game. There was an out of equilibrium response when we kicked the system with the electric field and we experienced the current. That was the out of equilibrium thing, which is described by the electric conductivity, an inherently time-dependent thing. And then if we waited long enough, then we reached the equilibrium distribution, which is described by how much this system is polarized. So it's the electric polarization or electric susceptibility which tells me about this response. So there are two different things in this game, the out of equilibrium one and the in equilibrium one. The same story can be told also for the CME. There will be out of equilibrium currents generated by a kick, and then if you wait long enough, there will be some polarization. Right. Let me go on. Now I'm the lucky one who can start to. What was your trick again, Andrew? Yes, that was it, I think. You have to go to that stairs. There was a mouse. No, there is no mouse. Actually, this is one of the most important slides, so if you have a question, then maybe. Right. Okay. So can currents at all flow in equilibrium? We will see that yes, under some circumstances they can flow, but they have to be local. There is a very general statement, Bloch's theorem, due to Bloch in the 40s, and then generalized to the quantum field theoretical context by Naoki Yamamoto in 10 years ago, which says that persistent electric currents cannot flow in the equilibrium, in the ground state of a quantum system. This applies to global currents, that means spatially averaged currents. It applies to conserved currents, and it applies in the thermodynamic limit, where you take the volume of your box to be very, very large. This theorem, in this case, will tell you that chiral magnetic effect cannot be there in the global system because it involves a conserved current, the vector current, the electric current. The chiral separation effect could be there because it involves an axial current which is not conserved. And there is a third bullet. Okay, I don't know. What shall I do? I could draw on the whiteboard. Or it moved, yes. So as I already said, the equilibrium CME is not possible because of the conservedness of the current. The CSE is possible. And the third bullet is that local CME currents are possible because the Bloch theorem only applies to the global current. So let's go over to the chiral magnetic effect in equilibrium. I'm talking about an electric current which is generated by the magnetic field. This you have already. And I told you that you need a chiral imbalance, and I would like to parameterize this chiral imbalance by this chiral chemical potential. It was introduced first by Kenji, Dimitri, and Harman Varinga, and it's a way just to parameterize chiral imbalance in the system. And from Bloch's theorem, we learned that this current should be zero. That also means that its expansion in the chiral chemical potential should be zero. So this CCME coefficient that I introduced here should be zero. But several results in the literature, if you look them up, they state that in equilibrium, the CCME is 1 over 2 pi squared. So what's going on with that? How is that possible? And the devil is in the details, and in this case the details are the ultraviolet regularization. So let's look at one particular example to see where things might go wrong. Let's look at the vacuum thermodynamic potential in the presence of a chiral chemical potential and the magnetic field. You can find the exact Dirac eigenvalues in this setup. You can construct the vacuum thermodynamic potential in this setup, and it will look something like this, where I separated the lowest Landau level, which is going to be relevant for us, from the rest. And the energies are there. This is what you can calculate exactly. And now you can derive the current by looking at the change of the thermodynamic potential if you change infinitesimally the vector potential in the A3 direction. And there is an ingenious trick that you can actually find the same thing by differentiating under the P3 integral with respect to P3. And if you do that, then you realize that you just need the integrand at infinity minus infinity. So that's the result. What is the result? Unfortunately, it's ill-defined because this is an improper integral. You cannot just read off the result from here because it involves infinity minus infinity. So to go on, you need to regularize. This is very standard in quantum field theory. And if you regularize with a cutoff, then you find that if you do it symmetrically, then the cutoff actually cancels and you end up with 1 over 2 pi squared for your CCME, which is not the correct result. The correct result should be 0, as we found from Bloch's theorem already. Why is that? That is because cutoff regularization is not a gauge invariant regularization in quantum chromodynamics. It is not consistent with word identities. Let me highlight the same aspect now from a slightly different point of view. All of these chiromagnetic effect conductivities are rooted in the triangle diagram, right? Because they have to do with axial anomaly. The triangle diagram looks like this. So this is basically, I'm taking the current, differentiated with respect to the magnetic field and the chiral chemical potential. Then basically I already get this coefficient that I'm after, and then I have 3 legs, a vector, and the axial vector leg. There are 2 triangle diagrams, and indeed you can find the CME coefficient by looking at a particular zero momentum limit of this diagrams. Why zero momentum limit? Because you want homogeneous magnetic fields, homogeneous currents, homogeneous chiral chemical potentials. On the other hand, the same triangle diagrams also appear in the axial anomaly, right? You just have to contract the diagrams with the momentum that flows in on the current leg. That's a textbook calculation, actually. Now, if you want to evaluate these diagrams and calculate the axial anomaly, and you don't use any regularization or a non-gauge invariant regularization, you will find that the result is just the pseudoscalar operator on the right-hand side. That is not the correct anomaly. The correct anomaly would have the FF tilde on the right-hand side, which is the term that comes from the variation of the measure in the Fujikawa approach, for example. In order to see that term, you have to use a gauge invariant regularization, and for example, Pauli-Villars or dimensional regularization. Pauli-Villars is a little bit easier for us in this case, so let's use that. In QED, you have to introduce 3 regulator species, 2 bosons and a fermion. Their masses goes to infinity. You do the calculation. That means that you have to take into account those regulator species in your diagrams. They contribute in a way which is shown on in the blue term. And if you take their masses to infinity, what you end up with is FF tilde with the correct coefficient. So what we learn here is that even though the unregularized result is finite, it is not correct, because there's a finite correction which comes from the anomaly in order to make the axial anomaly exactly its correct form. The same thing for the CME coefficient you can do. If you do it with the unregularized version, you find that the result is 1 over 2 pi squared. If you include the Pauli-Villars species which contribute, you find that they contribute with the blue term. The bosons and the fermions of these species contribute with different signs, and if you sum over everybody, as you should, you get 0. And so what we find here is that in equilibrium, which is what this calculation is about, the CME coefficient vanishes because of the anomaly. The anomaly holds. That means that the CME coefficient vanishes in equilibrium. That is the statement here. Okay, maybe this is not a surprising finding because you expect it from the beginning, but there is one particular result in the literature, lattice simulation in equilibrium, which showed a non-zero result. This is a seminal determination of the current about more than 10 years ago now. And here, what you can see in this from this result is the electric current is a function of the magnetic field, and the red points is what you want to look at. It's at finite chemical potential. And you clearly see that there is a slope. So this slope is the CCME. If you plot it on the right as a function of the lattice spacing, then you see that it is non-zero. Lattice simulations are done at finite lattice spacing, so these are the finite simulations, and optimally one then would like to do a continuum extrapolation where the lattice spacing is sent to 0. This was not done here because the lattice spacings were not fine enough, but you can clearly see that the result will be somewhere between 0.02 and 0.03. That's actually half of 1 over 2 pi squared, not even 1 over 2 pi squared, not even 0, but it's clearly non-zero. So what is going on here? This actually cost us quite a bit of time in order to understand how it is possible that this equilibrium result is not respecting Bloch's theorem. It's not respecting these perturbative arguments that I showed you. And the reason for that is actually that in these simulations, a non-conserved electric current was used. On the lattice, there are different ways to discretize your observables and your operators, and there is a version for the electric current which takes this naively correct form, but actually on the lattice this is not conserved. This is a form where the fermion and antifermion fields are defined at the same point. There is, however, a conserved version which looks like this, where the fermion and antifermion fields are defined at slightly shifted points, so-called point split current, and then there is also a gluon field in between them to connect and make them gauge invariant. Usually, both of these operators are fine if you look at, for example, hadron spectroscopy. You want to find the mass of the rho meson. Both of these operators will do the job. But in this particular setting, it is really important to use a conserved current. Remember, Bloch's theorem said that if you use a conserved current, then your consequences or your implications will apply, but not if you use a non-conserved current. So what we did was to redo these calculations with both the non-conserved current and the conserved one. So the red points here are the ones from the previous plot, and the black points are our calculations of the same setup. even though with a slightly different method, but the same setup. And you can see that we reproduce the results of Arata Yamamoto if we use a non-conserved current. But if you use a conserved current, then we go back to 0, which it should be. Okay. So then we went on to the complete setup, where we have full QCD interactions taken into account using the conserved electric currents, dynamical staggered quarks with physical quark masses, and here is the continuum limit is actually this yellow band, and we see that all our simulations satisfy that the CME current is 0 actually globally. Here we also use the different setup with Wilson quarks, a different discretization. We also spent quite some time in order to match both of these discretizations so that they are correct, and we see that all of these results give a 0 global CME current in equilibrium. Okay, so I hope now I convince you that all these mismatches or inconsistencies in the literature are now clarified. We understand why the inequilibrium CME coefficient should be 0, and it is 0, and all the methods agree on that. The chiral separation effect is a very, very similar thing. Let me very, very briefly just show you what the results are there. Here you would have such an equation where you have an axial current due to a magnetic field and the normal chemical potential. The axial current is non-conserved, so Bloch's theorem doesn't exclude it to be non-zero. The regularization on the lattice is also problematic and complicated here, but it's not as intricate as for the CME. There are also previous lattice efforts which we can build on, and here are the results for dynamical staggered quarks with physical quark masses in the continuum limit. You see that there is a suppressed current or coefficient, then a rise around 150 MeV, where the quark-gluon plasma arises from the hadronic phase via the crossover transition, and at large temperatures we assume approach 1/2 pi squared, which is the massless free case contribution. Also, we redid the calculations with Wilson quarks with a different setup, and we observed the same results. So this is, again, I would say, very well funded by now that the result looks like this. There is a comparison here to a baryon gas, or a hadron resonance gas type of model, which we did at low temperature, which also agrees with our results until low temperatures where it is valid. All right. So is there no hope? If we are in equilibrium, are there no chiral magnetic currents at all? Not really. Remember that Bloch's theorem was speaking about global, so spatially averaged currents. And we can look at local currents as well on the lattice. And that is actually even more relevant if you think about how the magnetic fields look like in a heavy ion collision. Heavy ion collisions have completely inhomogeneous magnetic fields. This is a magnetic field profile in the transverse plane, and you can see that the magnetic field is very strong in the center of the collision, but it decays towards the edges. So all of the lattice simulations I showed you earlier were using homogeneous magnetic fields, which is very far from this setup. But we can do better. We can use magnetic fields which have an inhomogeneity in them in one direction for the moment in this kind of setup, where we mimic the magnetic field as a function of x, which is the impact parameter direction in this plot, to be 1/cos squared. Some of you will like this profile because for this profile the Dirac equation can be solved exactly, and then you can find you could also treat it analytically if you want. So the profile looks something like this on the right, and epsilon tunes the width of this range. It should be around 0.6 Fermi if you want to make contact to those heavy ion collision plots. We already have some expertise in our group in how this can be implemented on the lattice and what kind of effects it has on thermodynamic quantities. So, what do we have to do? We have to calculate the current as a function of the chiral chemical potential and the magnetic field. This was the previous equation where there was only one coefficient that appears in this game, to leading order. Now we want to go beyond this because now the magnetic field is x-dependent. That means that instead of just b times the coefficient, we will have a convolution in coordinate space like shown on the right hand side. In momentum space, this would be just a simple product. So we have this convolution, which means that the current will depend on x1 in this kind of form. Now Bloch theorem tells us that the total spatially averaged current should be 0. So if we average the so obtained current, it should be 0. But x by x or x1 by x1, it can be non-zero. Here is a little cartoon, not cartoon, it's actually actual measurements in the non-interacting theory, so where I don't have gluons, I just have quarks and antiquarks. What is shown here is the value of the current, the blue dots, as a function of x, and the yellow band shows you the magnetic field profile. So if you have a homogeneous magnetic field profile, which is this constant orange band, then you have 0. Not just on average, but also point by point you have 0 because you have translational invariance if the magnetic field is constant on the level of gauge invariant quantities, which the current is. But if we now make the magnetic field inhomogeneous, according to this 1 over cos squared profile, then you can see that some kind of response is emerging. And the more inhomogeneous you make the magnetic field, the more peaked, the more structure emerges in the local currents. These local currents are always such that their integral over x1 vanishes due to Bloch, but x1 by x1 there is a non-zero result. So this was just for free fermions. This is not the full story. So let's go to, this is one more plot in order to clarify the direction of these currents. So the magnetic field always points in the x3 direction in our case, in our notation, but its magnitude varies as a function of x1. And what we see here is that the currents also always point in the x3 direction, but their magnitude and even their sign varies as a function of x1. So hopefully now you see the effect as visualized by these arrows. So this was the free case, but we can go over to full QCD using dynamical staggered quarks with physical quark masses, doing the continuum extrapolation, carefully watching that we are using the conserved electric current as it should be, and this is the result here for different magnetic field values at a given temperature which might be of relevance around the QCD crossover, and you can see that one has a very similar profile. Okay, there is a currents which flow opposite direction in the center of the collision and slightly towards the edges. Okay. Interestingly, what we find is that if you look at the maxima of these curves, the central value and the value of it around the edges as a function of the magnetic field, then we have a linear region, and the for different temperatures, this linear behavior is very, very similar. Actually, there are different temperatures here involved, and they are on top of each other. So the response seems to be, to a very large degree, temperature independent for this range of temperatures. This got us thinking why this is the case. What is shown here is now in a slightly different form the same information. So this is the value of the central point as a function of the temperature at a given magnetic field, or the slope of the with respect to the magnetic field actually. And the red line is a hadron resonance gas type of model prediction for this observable. So what we can see here is that hadrons contribute to this observable in a roughly temperature independent way. And this is why the result is roughly independent of the temperature, because these hadronic constituents just respond to this kind of magnetic fields in this manner. So, what does this have to do with potential experimental detection? Can we say something about that? Well, we have such a profile now where the electric currents due to the local chiral-magnetic effect look like this in the transverse plane. So this will be the transverse plane. And clearly this can affect the outcome of, for example, a collision. If you have a hydrodynamic flow which will produce outwards pressures, then instead of having such a completely isotropic situation, we can consider these currents as initial conditions for the hydrodynamic expansion. And in that case, you will have an anisotropic way that the plasma will expand. And that will give rise to to azimuthal angle dependent outcomes. This seems like a very tricky quantity to look at because it requires acceptance cost, not just in pseudo-rapidity, but also in the transverse plane as a function of the azimuthal angle. Nevertheless, we hope that these results might guide the experimental efforts further beyond that what we have seen today already. Good. If I have 2 more minutes, then all of what I said so far was about the in-equilibrium chiral-magnetic effect, right? So clearly there's much more than that. there is the out of equilibrium effect, the out of equilibrium response, which I started the whole talk with. And this is going to be discussed in the next talk by Eduardo Garnacho. And there you will see that using lattice simulations, we can also give a first estimate and results about how out of equilibrium CME currents should look like. And the second question that you might have is this chiral chemical potential that was introduced to describe the chiral imbalance. Can we do better than that? Can we, for example, consider the product of electric and magnetic fields which are parallel in order to generate chirality in the system? This is also possible, and I also urge you to wait for half an hour more for the talk of Javier Hernandez about that. But there you will see that this kind of backgrounds and E.B backgrounds have to do with something completely different, not the chiral magnetic effect, but axions in QCD. So I urge you to wait for that and check out what comes out of that. And that brings me to the summary. So I had a couple of take-home messages for you, which I would like you to try to remember. The CME is full of subtleties. It's full of subtleties both in terms of whether one considers in equilibrium or out of equilibrium effects. It is very important to distinguish between the two. And once we are in the in equilibrium situation, which is the simplest thing to look at on the lattice, very, very careful regularization is required. I showed you that this applies not just for perturbative calculations, where you have to insist to use a gauge invariant regularization, but also on the lattice, where you have to really insist that you use a conserved vector current. And we managed to clarify a long-standing inconsistency in the literature by pointing out this issue. But there is a way out for chiral magnetic effects in equilibrium, because you can look at inhomogeneous magnetic fields and then inhomogeneous responses, local chiral magnetic effect, chiral magnetic currents emerge, which have this kind of profile in equilibrium situations. And I also showed you results about the in equilibrium chiral separation effect, which is a way easier quantity to look at, and it shows you actually very nicely how strongly interacting matter goes over from a hadronic regime to a quark-gluon plasma regime, and actually it can also be used to define the pseudocritical temperature via an inflection point, for example. Thank you very much for your attention.
Thank you, Gergo. There are many hands raised, but I want to ask you first, otherwise I won't have a chance. I'm sorry, it's my privilege, I guess. You mentioned that these extra currents that you generate because of this effect that you showed it in equilibrium will distort the shape of the profile of the particles that are emitted. And this, of course, should reflect into a V2 measurement, which I don't know if it is subtracted. Do you guys take care of that? But maybe this is something to discuss later, but do you know of this? Is this experimentally already being implemented?
I think maybe Fuchan can say something about that.
But do you know, are you aware of that? Whether or not it is implemented like that?
I don't think that there is a...
Okay, sorry.
Yeah, I would like to make a comment exactly on this point. So it's really great talk. And I think that this in equilibrium local CME is really the first step in the development of chiral magnetic wave, where a local fluctuation of chiral charge gives this quadrupole deformation of electric charge. And experimentally, it is predicted to give rise to charge dependence of elliptic flow. And Star collaboration studied this experimentally by looking at this charge dependence as a function of baryon asymmetry at mid-rapidity. So they have observed this dependence as usual. I mean, there are lots of backgrounds and so on, but this is indeed very relevant for experiment.
Thank you for the encouraging words. But let me point out that this is for homogeneous chiral imbalance. The chiral imbalance is not inhomogeneous. The magnetic field is inhomogeneous. Yes. Actually, we can also make the chiral imbalance inhomogeneous, and then we have a way more complicated response that for which I have a backup, just to show the nice plots. So we can also do this on the lattice, both the magnetic field and the chiral imbalance. Yes.
Yeah, about the V2, I think there will be a very strong V2 background contribution, but you mentioned that the higher harmonics might be a way to go, and that's very interesting.
Yes,
Thank you very much for the intriguing talk. I do have a question.
Okay.
But go ahead.
I just wanted to point out that yes, if you look at this little cartoon which I made here, then you can see that there is a higher harmonics, which is somehow encoding this response. Go ahead.
On this cartoon, so experimentally, of course, it's easier just to cut on one thing instead of pseudo-lipidity and angle. It'll be more complicated. But I think because of this profile in the periphery, you don't have much CME effect, and those periphery particles go to more forward, backward. And the central region is more kind of end up in the middle rapidity. So maybe by cutting on the pseudo rapidity already, you can see effect like that. Yeah, no, I know. This is
rapidity is into the plane.
But the rapidity is into the screen, but the larger X region will go to more forward.
I think Fuchang says that these, so the blue arrows on the edge will be more affected by the
so there will be some differential effect.
Z direction.
Very interesting.
Thank you.
Thank you. Nice comment. More questions, comments?
So thank you for a very nice talk. So could you go to your summary page?
Summary.
Yeah, you have the local CME. And could you explain why in the middle the direction of the current is opposite to the global CME prediction?
First of all, the global CME thing is 0.
Yeah, the wrong global CME thing.
The wrong global CME thing is 0. That's true. Sorry. Yes. The wrong global CME is on the opposite direction. But well, why it's in the opposite direction? I think even this response. So this, as I said, for this kind of background, you can solve the Dirac equation exactly. So in principle, this blue curve you can get analytically. And it arises as a combination of the physical fermion and the Pauli-Villars species, if you do it with Pauli-Villars regularization. And then you will see that there's a competition between these two in such a way that if you make the magnetic field homogeneous, then the total result is 0. And if you make the magnetic field inhomogeneous, then there are cancellations. So why in the end the middle is negative and this is positive, I can't really tell you, but it arises from this competition between the physical fermion and the Pauli-Villars species.
Okay, thank you.
I hope that helps a bit.
Okay.
Thank you very much, Gergo. I'm afraid I have to cut again, but let's thank Gergo again. And now we call Eduardo.
Giorgio and Anna for the great organization. So I'm very happy to present some preliminary results, which I hope are going to be very exciting. And I also want to pose some open problems of things that we still have to understand in this project. So I would really appreciate any feedback or comment that you can give me, either in the questions part or also during the discussion later. So I think, as we already have learned today, anomalous transport are a very interesting type of phenomena. They arise from the interplay of the axial anomaly with electromagnetic fields or vorticities. And in particularly, in our group, we focus on the ones that appear due to the magnetic field. And as we heard, this would be, for example, the chiral magnetic effect or the chiral separation effect. But in this talk, I will focus mainly only on the CME. And as you already saw from Gergo's talk, the idea is to use Lattice QCD simulations to understand what are the actual CME properties in QCD. So as we already saw in the talk by Gergo before, these are the highlights of the project that we have been covering since 2023, I guess. And then the key word that I think Gergo emphasized many times is in equilibrium. So all these results are in complete thermal equilibrium. So the idea is, can we actually understand what are the actual out of equilibrium properties of the CME? And this will be really relevant, as we already learned today, because if we want to come closer to experiments, these out of equilibrium effects can be very, very important. So what I want to try to address in this talk is what can we say from Euclidean lattice QCD simulations about the out of equilibrium CME. So I want to start by, I hope a very simple idea, but I think it will help me building up to the CME. So we want to use linear response theory. So in very simple terms, we want to consider real-time correlators. So you can consider the retarded correlator, and then its imaginary part in frequency space is the spectral function. And then we have, on the other hand, some constitutive equation that depends on some transport coefficient that we want to calculate. The idea is that linear response theory, we can apply some time-dependent perturbation to the system, and then we can relate the transport coefficient that we are interested in with these real-time correlators. And then this gives rise to these very well-known Kubo formulas, which relate usually the transport coefficient with the slope of the spectral function at zero frequency. So this is, as I said, a very well-known story, and then this can be done to, for example, for the electric conductivity or the bulk and shear viscosities. And then since you can calculate these real-time correlators in the microscopic theory, then this gives you information about what are these transport coefficients in QCD. And then once you can, if you could calculate these coefficients, then you could use them, for example, in hydrodynamic simulations. Let me give an example, which I guess is the better well-known example, which is the electric conductivity. So in the case of the electric conductivity, we were to consider a current, so a vector-vector current correlator. And then we are interested in the, we can consider, for example, dissipative hydrodynamics, and this depends, for example, in the diffusion coefficient D. Then, using linear response theory, we can relate this diffusion coefficient via a time-dependent density perturbation with a density-density correlator, and also you can, if you want, relate it to a spatial, current-current correlator, so in the spatial components. And in the end, you can arrive at a well-known Kubo formula, which relates the diffusion coefficient times the baryon susceptibility, which is precisely the definition of the electric current, with the spectral function for the current-current correlator. And then I want to point out that this whole derivation also gives you some normalization that comes exactly from this diffusion equation. And then, as I said, this is all very well known, and this has already been used in, for example, Lattice QCD to calculate the conductivity in QCD and also the conductivity at finite magnetic field. Now, the idea is to do something similar, but now for the CME. In this case, we will be interested in considering this type of correlator, which has already appeared in the talk by Gergo before. Now, this is a vector current correlator in the direction of the magnetic field, and then a correlator that has the axial density here. And everything now here has to be done at finite homogeneous magnetic field. Then again, we can define the spectral function that is related to this correlator, and now we would like to apply linear response theory to this. Unfortunately, this is one of the missing parts in the project so far, is that we need to connect, in this case not normal dissipative hydrodynamics, but we have to connect it with chiral hydrodynamics. So we will need to connect this correlator, this real-time correlator, with the coefficient that appear in the hydrodynamic equations in this theory, which so far, it's not that it cannot be done, so far we have not done. Nevertheless, we can still consider which type of spectral function would arise for this type of analysis, and then we can define an out of equilibrium CME coefficient, which would be again related to what is the slope of the spectral function for this CME, so the one that comes from the vector current with the axial density, in complete analogy for what I said about the electric conductivity. So I want to point out two issues. One I already said, that this connection is missing, and the other one is that since this is just a definition, then the normalization for the Kubo formula so far is just arbitrary. This should come from a careful analysis in this connection here. Although this, one of the nice things about these spectral functions is actually they can be calculated fairly straightforwardly at one loop. So this is a well-known calculation. For example, in the case of the electric conductivity, so this is now exact only for free fermions, so you can just think about a system without QCD interactions, just free fermions, and then the derivation for the electric conductivity is well known, and then you get this result here, which I can guide you through. So you have a term that arises because of decay, so you have this only a threshold, which you only have when you have two particles of mass m. So this has contributions both from the vacuum and from the thermal part. And then you have this part here, which is proportional to a Dirac delta and to the susceptibility, to the baryon susceptibility. And this is purely a thermal contribution. So this at 0T, this doesn't appear. And then if you just want to blindly apply the Kubo formula that I showed you before to this spectral function, what you will find is that you essentially hit the Dirac delta that you have here, and essentially the conductivity diverges, which is not a surprise because this is just a system of free fermions. So the mean free path is just infinite, so the conductivity blows up because of this. When you introduce interactions, then this is no longer the case. Then this delta here essentially smears, and then you get a finite conductivity. And then a way of understanding this using perturbation theory is that actually you need to introduce some type of resummation, which makes this finite. So this is the, for example, well-known procedure by Arnold, Moore, and Jaffe in the case of the electric conductivity. Now we can do the same for the CME and calculate at one loop the spectral function, and this is what we presented in the last Lattice conference. So we have a very similar spectral function. I want to point out first that this is proportional linearly to the magnetic field, as one would expect. Again, there is this decay part, which is similar to the one in the electric conductivity, although in this case, here it diverges at high frequencies, but here this one doesn't diverge. And now we have, again, another term that is proportional to a Dirac delta. And then the coefficient of the Dirac delta in the case of the conductivity, of the spectral function of the conductivity, was just the susceptibility. But in the case of the CME, you get this coefficient here, which is again m over t dependent, and then I plot here for you to see. What you see is that in the massless limit, this coefficient is precisely 1 over 2 pi square, 0.05, this famous number that we have seen a couple of times today. And then when you make the free quarks heavier, then this coefficient actually goes to 0. So one thing that, again, you can go and then apply the Kubo formula that I showed you before to this spectral function, and then you will find again that this coefficient just blows up, which tells you that in the same fashion as the electric conductivity, this requires some resummation, or the introduction of some interactions. However, the sole fact that this resummation is required, it tells you that the relation of this spectral function to the axial anomaly is something that we also have to understand. A bonus thing that we can do is that we can only not do this for the CME, but we can actually also do it for the CSE, which we also showed in the contribution to the Lattice conference. And then here, actually, it has a very interesting characteristic. In the case of the CSE, there is no contribution from the decay part, but there is only purely this thermal part with the delta, which is precisely the same as the one for the CME. And this has an interesting it provokes that the CSE correlator now, if you look, is going to be tau independent, essentially because of the spectral representation. If you plug in the spectral function for the C in this case, this will imply that the CSE correlator has to be tau independent. So I will come back to this, to a consequence of this in a second. Okay, so as I said, the idea would be to do this from the lattice. Unfortunately, on the lattice, you cannot directly calculate real-time quantities. You can only calculate Euclidean correlators. So one way to obtain information about the real-time quantities is using the spectral representation. So I guide you through here. You can actually express the Euclidean correlator as a function of the imaginary time, which is what you can get from the lattice, in a convolution with the spectral function, which is exactly what you would want, convoluted with a kernel, which is just a function that is known. Unfortunately, if you do this on the lattice, especially if you do it at finite t, the number of points where you know this correlator is very limited. Usually, you can think of it more or less having of the order of 10 points. And then you would like to know this function smoothly, because you would like to extract the slope. And essentially, this is just an ill-posed problem, because I want to get a smooth function in a convolution, and I only have of the order of 10 points. But this is, as I said, a very well-known problem on the lattice. This has been applied to get other transport coefficients, for example, the electric conductivity, as I mentioned, but also the viscosities. And there are many methods that have been developed over the years by the lattice community and other communities to solve this type of inverse problems. For example, maximum entropy method, Backus-Gilbert, and then more recently there are also machine learning algorithms that help to diminish the ill-posedness of this problem. However, this is not what I want to do first, because as I just said, this is very complicated. I want to first use an easier estimator for the conductivity, and for this I would use the so-called midpoint method. So the idea is that the kernel here, which is what I showed you in the convolution before, has this form here, so it's a cos over sines, and I can evaluate the kernel at the midpoint, at the temporal midpoint of the lattice. And essentially this will give me this type of function here. And then this means when I take the temperature to 0, this kernel smears, peaks, and then at 0 temperature, this essentially becomes a delta at centered in the 0 frequency. So essentially this tells me that towards 0 temperature, the midpoint of the Euclidean correlator is going to give me an estimate for the conductivity, because this kernel, when I go to 0t, will essentially pinch exactly the part of the spectral function that I want. So here, what we did, actually this was also already posed by Pavel Bubidovic in a paper last year, is that in order to estimate this out of equilibrium conductivity, one can look essentially at the midpoint of the correlator, multiply by some factors. And in particular, there is this factor of pi that I will come back in a second. So here I show you results for this midpoint estimator. As I already told you, this is only a good approximation when I am at low temperatures, because this is the only setup where I'm essentially pinching the correct thing. But at high temperatures, it's not clear what this estimator is going to give me. So here I show you results both with quenched Wilson fermions and with QCD, with staggered fermions in physical QCD. So this is QCD at the physical point. And then what you can see in both cases is that when you go to lower temperatures, this estimator actually multiply times pi, for a reason that will become clear in a second. This becomes suppressed. So essentially you see that when you go to 0t, this is 0. So this is already a very first clue that the CME, this out of equilibrium conductivity, is suppressed in the lower temperature regime. And I want to also give you an intuition of why. As you can see here, I plot this line, which is essentially 1 over 2 pi squared, and I can actually explain to you why this goes to, at the high t, this seems also to go to 1 over 2 pi squared. And this can be understood because if I take the estimator and then I multiply by pi, so essentially I take this quantity here, this is, you can show that at one loop in perturbation theory, this is exactly the coefficient of the CSE for free fermions. Which, when you go to the masses limit, as we also showed in the talk before, this goes to 1 over 2 pi squared. So essentially, this tells you that at high t, this observable is also going to go to 1 over 2 pi squared precisely because of this. However, can we do better than using only one point of the correlator? So the answer is yes. The idea is that if still you don't want to use reconstruction method, one could use an improved estimator using not only one point, but using several points. So the idea is that this is the derivation that I didn't show you before, but if I consider the Euclidean correlator evaluated at the midpoint, this C1, which is the first term in a Taylor expansion of the spectral function, is exactly the coefficient that I'm interested in, but it is, so to say, contaminated by higher orders in the temperature. It has contributions from a T cube that is also proportional to the term that goes with the omega squared, etc. So the idea is that this expansion here can actually be done for any point of the correlator that we can obtain on the lattice. So essentially, this first line here will give me the coefficients of the, so these coefficients here are essentially these ones. And now I can play the same game not only for the midpoint, but for any point on the lattice. Obviously, the lattice has a finite size, so this has to be truncated at some point. There is a maximum number of points that I can use. But now I can express it like this, and this is just a system of equations that I can solve. And then by solving this actually gives you a better estimation of C1, because you can imagine that you can obtain these other coefficients and essentially you can eliminate them from your estimation. And I can show you an example of how this works in a toy model. So you just consider a very simple example of a spectral function, which is a Breit-Wigner. So this is just the toy model for a Breit-Wigner. And then I defined the conductivity that I would be interested by, again, as the slope of the conductivity of the spectral function at 0 frequency. And then here on the right, you can essentially you have the spectral function, you can convolute it with the kernel and get Euclidean correlator. And here I showed you the estimation of the conductivity in this case, and then you see that if I only use the midpoint, so if I only use 1 point, the estimation from the exact result, which is this line here, is far off. However, if I include more and more points, and then I include this improved estimation with multi-points, then this goes closer to the exact result. So this tells you that this multi-point method improves the estimation of the conductivity. So this is good news. Then we have a way of improving our estimation, and then we can do this. So here I show you this method applied to the Quench-Wilson points that I showed you before. Here I choose to show only one lattice, and then here these points, the lower ones, are the ones that you get from the midpoint. So these are the ones that I showed you before. And now this is exactly the estimator of the out of equilibrium conductivity. And when I include more points, so when I use 2 or 3 points, the conductivity actually goes up. So a high T, this tells us that in Quench-Wilson fermions, this CME conductivity is around 0.022 or 0.025, more or less. But of course, this is just an estimator. Can we actually do better than this? And then the answer is that yes, of course, you will have to end up doing a reconstruction. And this is what I'm going to show you now. This is still preliminary work, but I think it's already very exciting. So let me guide you through this. So what we did is using the staggered fermions in QCD. So we chose only one temperature, so 300 MeV. We actually calculated the Euclidean correlator for a wide variety of lattices for several magnetic fields at this given temperature. And then we can use a particular method to reconstruct the spectral function. In particular, we just chose these Gaussian processes. And then here I saw the results. So if you go up here, this is higher NT. So essentially going in this direction is going to the continuum limit. And then you see first that for all the lattices, the behavior of this estimated conductivity is very flat with the magnetic field, as you would expect. So this tells you that, as I discussed for free fermions, the conductivity is linear. It seems to be linear even for higher magnetic fields, with the magnetic field. And then once we had this value, we can actually draw a first continuum limit estimation of this. So here I saw different values of the lattice spacing, and then I showed you an estimation using these values here, and then this goes more or less to 0.023, which, if you remember the numbers that I saw for the multi-point estimator, it is in the same ballpark, which is already a very interesting first hint that the result can be trusted. Of course, although I think this is very, very exciting, I will emphasize that this has to be taken with a pinch of salt, because these reconstruction processes are very tricky, and then there has to be a very careful systematic error estimation. So this is something that we have not carried so far, and then we plan to not only use Gaussian processes, but also use several other methods to be sure that the reconstruction process is under control. But again, I want to emphasize that this is the first time that we have access to this type of out of equilibrium CME conductivities in QCD, and then both independent methods actually seems to converge to the same point. So I think this is already very good news. And this takes me to my summary. So I show you how can we study the out of equilibrium CME conductivity on the lattice. I also give you an exact expression at one loop in perturbation theory for the spectral functions, both of the CME and the CSE. And then the first estimation using this midpoint method tells us that this out of equilibrium conductivity has to be suppressed at low T. And then we have already preliminary results going towards the continuum limit at high temperature, so at 300 MeV. And then this, as I said, for me, this is very exciting good news. However, as I hope I conveyed, there are several open questions that I would love to discuss with you. So how to actually obtain a proper Cuba formula from chiral hydro, and then what is the actual relation between the required resummation in the spectral function that I showed and the axial anomaly. And then as an outlook, of course, we would like to apply different reconstruction methods and not only concentrate on one temperature, but also do a scan in temperatures, which hopefully will give us an idea of the out of equilibrium conductivity of the CME in QCD. So thanks a lot.
Thank you, Eduardo. Now the floor is open for questions.
Yeah, so very important results. I just want to make a very simple point, linking your results to the talk by Juan. So the fact that CME conductivity gets suppressed below the critical temperature is consistent with the absence of CME at low collision energies when the plasma is not formed. So I think this is a really important confirmation of this.
Thanks for the comment.
More questions, comments? Leticia?
Yes. So thank you for the nice talk. So I've seen spectral functions reconstructions in other contexts, and I understand that it's quite complicated. So in the end, the last plot you showed is using, you said Gaussian processes. Would this be related to maximum entropy method, or you're still using the previous procedure you showed?
So it's closer to a, so it's actually, it's closer to a Backus-Gilbert in the sense that it's a linear combination of the actual points of the correlator, so it's not a Bayesian analysis in that sense, but this is just a parameterization of the reconstruction, of the required reconstruction in terms of a Gaussian process, and then again, you have some free parameters that you have to tune, and you can do an optimization of this. You can look for the optimal parameters in the hyperspace, and then you find this is what we did, and then this is what we find. But of course, that does not tell you the whole story about what is the actual systematic of the estimates.
And I also have another question, because actually for the transport coefficients, you usually need to take the omega to zero limit, right? So it's an infrared, deep infrared quantity. So are you worried also about the having a large lattice and investigating systematic effects related to this?
Yeah, I think this you see already here, right? That the fact that in a staggered, actually, okay, there is a technical reason why it's even more important to have not only final lattices but also higher number of temporal points. But here you see that it's important that, okay, sorry, that it's important that you go to a higher and higher number of temporal points in order to obtain a unreliable estimator for the conductivity.
More questions, comments? If not, let's thank Eduardo again.
And the relation with electromagnetic fields and topology. And this is some work that I've done in collaboration with Bastian Brandt, Gergely Endrodi, Gergely Marco, and Lauren Panulo. So let's dive into it. So this is basically the result that we obtained for the coupling, for the model independent contribution for the axion-photon coupling. So let me show you first how we got there, and in order to do that, I'm first going to introduce what is the strong speed problem and how axions come about. Then I'm going to talk a bit about the axion-photon coupling itself, and then I'm going to do some lattice definitions of the coupling and the corresponding results. And to finalize, I'll discuss a bit the effect of these results on the current model bounds. So what is the strong CP problem? So first, we know that in the QCD Lagrangian, we could have potentially these two sources of CP violation, of which only the sum has a physical meaning, since we can do chiral rotations and move the theta terms from one side to the other. But we know that the strong interactions are invariant under charge conjugation and parity. And in particular, one result is the neutron electric dipole moment that we can compute both on the theory side and also obtain it experimentally. And that gives us a bound on the total value for theta. And this strong CP problem is asking, why is theta so small? So how do axions come about into the picture? So there are a lot of solutions for the strong CP problems, but axions are actually one of the most versatile ones, since not only do they solve the strong CP problem, but also they are potential dark matter candidates. And the basic idea is to have a new global U1 symmetry that it would join the QCD in such a way with coupling directly to the gluons and then some model-dependent interactions. And the introduction of a new free parameter, this axion decay constant. So the whole idea is that the axion field would relax, And in doing so, it would cancel the CP violating term. And moreover, at this potential here, it's not flat at low temperatures. It actually develops a mass, and that mass is nothing but the topological susceptibility of QCD that has been well determined both perturbatively and also on the lattice. So we are interested in the axion-photon coupling. And why in this one? Because we have, actually there are many types of couplings with the axions, not only to photons, but to nucleons and to new extra particles, model-dependent particles. But this one, I think, is one of the most relevant ones because it's involved in a lot of experimental efforts, such as this one in CERN. And what exactly can we do on the lattice? So the coupling has such a form with the axions and a CP-odd combination of the electromagnetic fields. And one can see that it actually has two additive contributions. One model dependent that is related to the anomaly coefficients of both electromagnetism and the strong interactions, and a model independent part that it receives only contributions from QCD. And this is one of the chiral perturbation theory results that, if you remember, the result that we computed is actually quite close. So now the question is, how can we actually compute this coupling on the lattice? So we know that the coupling has such a form. So then the natural definition would be to compute three derivatives with respect to the partition function, with respect to the axions, and with respect to the electromagnetic fields. So in principle, we have three different types of correlators that we can compute. And we've decided to go for the simplest one, which is just a topological charge, which you can easily see by noticing the resemblance between the axion field and the theta parameter. And we basically then obtain that the coupling is nothing but the slope of the topological charge with respect to a CP-odd combination of electromagnetic fields. And this is basically the one of the gluonic definition that we're gonna use. With respect to the other correlators, we did some preliminary studies, and we actually noticed that for the same amount of statistics on the lattice, the correlator between the topological charge and an electric current is way noisier, and we expect that the correlator with the two currents will be even much noisier. So we decided to stick with this one. And also notice that this coupling, at least for vanishing electromagnetic fields, for very weak fields, it's also a ratio of the gluonic and the electromagnetic topological charges. And this prompted us to ask, is there an alternative way to define these topological charges, not only by computing them directly? So there's a way, and it's through the actual word identities. So we would have, by introducing this CP-odd combination of electromagnetic fields, not only a contribution from the gluons, but also from the electromagnetic fields to the anomalous word identity. And we can integrate this over the whole lattice. And since we are working with periodic boundary conditions, we get 0 on this side. And then we see that we have an equation relating the topological charge, the CP-odd combination of electromagnetic fields, and this pseudoscalar condensate. And we can see then that if we measure this observed on the lattice we can extract the topological information in a different way. So now the question that you might be asking is, in that equation, the two effects, the gluonics and the electromagnetics, are intertwined. So the natural question is, how can we separate those two contributions to effectively use them on the definition of the coupling? And the idea is behind the valence and the C contributions. So we're gonna have some C effects from the quarks coupling to the gluons through the determinant, and then also on the valence part for the operator that we want to compute. And the thing is that on the lattice we have the liberty of using different operators for each of the sides. So we can play the game of turning on and off the electromagnetic fields on the C part. And basically by doing that, then we can get two equations, one for the expectation value of the topological charge in an E dot B background, and another one for the electromagnetic fields by computing this on a zero electromagnetic fields background. But notice that the electromagnetic fields need to be present here in order for the pseudoscalar condensate to fill the electromagnetic field. So if we now take the definition of this, basically this ratio of the topological charges, we basically arrive at this result where we have that the leading order dependence in the electromagnetic fields of this ratio of pseudoscalar condensates, it's the axion-photon coupling. So now let me show you some some lattice results. First at finite lattice spacing. So so this is the setup that we are using. We're using 2+1 staggered quarks at the physical point. And on the left-hand side, you can see the results of for a gluonic definition. And as you can see, we obtain linear dependence for these values of the electromagnetic field. So here I'm showing you just a representative fit of the many that we do here, because if you notice, the Taylor expansion is not only, it does not only have E dot B such terms, but it can also have CP odd terms that also have, for example, E squared plus P squared terms. So in reality, we have a surface in the E and B space. So with them, we do many fits, allowing for all possible different combinations of points and of orders of the Taylor expansion. And that's also why we have a bit of these oscillations around the linear expected behavior. And a similar thing happens here on the fermionic side. Well, the leading order behavior is this. We expect that it's a constant, but as well, since we cannot really get to one of the corners of the space to the zero side, we still have these oscillations with respect to the expected behavior. But still, as you can see, the values they nicely approximate what we were expected. So now we've repeated this for other lattice spacings, and these are the results. So as you can see, in the coarser lattices, there's a stronger dependence with the lattice spacing, but once we get to below 0.05 Fermi squared, linear behavior sets in that it's allows us to take control continuum limit. And we repeat the same for the fermionic side. Well, we've considered many definitions for the pseudoscalar condensate, namely with only the U quark, only the D quark, only the S quark, and a linear combination of the U and D quarks. And as you can see, the continuum limit extrapolations are not only in very good agreement with each other from the two methods, but also they are very close to some other chiral perturbation theory calculations. And before you ask me later, let me tell you what these asterisks next to the chiral perturbation theory calculations are. And the thing is that in our simulations, even though we are at the physical point, we are simulating 2+1 fermions, which means that the U and the D quarks we are considering to be actually degenerate and in mass. And the reason for that is that usually the isospin breaking effects, they are really small, but actually for topological observables, it can be that they are really sensitive to the small difference between the U and the D quarks. And this is actually the case for the axion-photon coupling, and we can see this through chiral perturbation theory. And if we compute a ratio between the coupling computed at the physical point with respect to the symmetric point, we see that the physical point is actually around 20% bigger than in the symmetric case. So what we've done is we've rescaled our calculation with this factor in order to take our result to the physical point. So we are not the only, this is not an idea that we on our own. Actually, a similar correction is done for the computation of the topological susceptibility on the lattice. And after doing that, we get to this result, which it's the first non-perturbative calculation of the axion-photon coupling for the model-independent contribution. And here I give you some results from several chiral perturbation theories with 2 and 3 flavors, and also from this using the U3 symmetry group. And as you can see, our result is pretty close to all of them, especially to this third prediction. So now, how does our value affect the current bounds on the models? So the first thing is to ask what is the width of this yellow band in the PDG? So the width of this band comes from basically considering different hadronic models with this range of models. And where does this range come from? So they consider several models that minimize and or maximize the magnitude of the full coupling, taking into account the QCD contribution, and with these two criteria. So basically, one, that the quarks introduced in the new model, they are sufficiently short-lived, and also that they not induce a Landau pole below the Planck mass in the running of the couplings. And does our result change this range of the model? So it actually does not, and this range stays the same. So what happens in a more visual way? So here we have an extrusion plot using some experimental data, as well, some experimental data, and we show here the model-dependent contribution with the bounds that I showed before, and as well with our value for the coupling, which, as you can see, is really, really close to the lower bound for the possible models. And also one point that I would like to highlight here is that any point that lies, any model that lies close to this line is gonna be severely suppressed. So it's gonna be really difficult to detect. And we've also included this calculation for the allowed masses for the axion, taking into account some consideration from how which percentage of dark matter they contribute to, done from the BMW collaboration based on the calculation for the topological susceptibility. And as you can see, the combined region between the allowed masses by their work and the allowed models, it doesn't, and the allowed models, it's still not on the current investigations, although in the future experiments will try to go down into this region. And now with respect to the total coupling, so our result ends up looking like this. So again, we have a width given by that range of models, and also there's a big region related to the allowed masses by the Wuppertal calculation, and also ours that is not yet under the experimental constraints. And so this gives me to the end of the talk. So I have shown you the first non-perturbative calculation for the model independent contribution to the axion-photon coupling. And I've also shown you how the results of our calculations affect the current bounds for the total coupling. So thank you very much for your attention, and I'm looking forward to your questions.
Thank you, Javier. Questions? Enrique?
Thank you for a very nice talk. So I have a rather conceptual question. If you think about the anomalies as from the Chern-Simons action point of view as surface terms, because the Chern-Simons term is an exterior derivative, so topologically speaking, it's a surface term.
Yes.
But then for technical reasons, you implement calculations in the lattice by using periodic boundary conditions, right? And that's why Bloch's theorem, comes into, because you don't break the translational symmetry in the lattice. But then the question is, how is it, both pictures, the fact that you're trying to predict a surface-related property by using periodic boundary conditions, how does this somehow work?
Yeah, so that's actually a really good question, which I don't know the details about. I know that there are some proofs of, okay, the lattice is also not a manifold, but there are some ways to show that you can actually have also topology on a compact manifold. But it's true that there's not a direct connection between these surface terms and the periodic boundary conditions that we're using, but there is indeed a way to show when you have a compact manifold that you can actually have topologically non-trivial states for the gluon fields. I mean, we can discuss it later. I can look up the reference and show you later.
I need to cut it short again. I'm sorry, Kenji. There is going to be discussion later. So thank you very much again, Javier.
Thank you.
Now we have an online talk by Aritra Bandyopadhyay. Aritra, are you there?
Mateo, can you hear me?
Now we can hear you.
Okay.
Can
okay.
you
Sorry.
Can you show your
I don't
slides?
know. Yeah.
Just 1 minute, we have a little problem here, okay?
Okay, so hold on a second, Aritra.
Okay. I'd like to thank the organizer for giving me this opportunity, and I also think able to go there in person. It's always a loss not to be able to go to Brazil in person. So with that, I will start by mentioning that this is an ongoing work where we study the effect of the local acceleration in dilepton production rate. This work we are currently doing with Maxim Chernodov, Victor Ambrush, and our first year PhD student Moulindu Kundu. Okay, so we all know about the basic stages of the heavy ion collision. It gives us a multifaceted quantum system, which is initially far away from equilibrium and rapidly expanding with self-interaction. And so with all these important stages like initial conditions, equilibrium, QGP, hadronization, freeze-outs and everything, if we want to know more about these stages, so we need to probe this system, and these probes, we call them signatures. For example, if we want to probe particularly QGP, we call it QGP signatures. Now there are different kind of probes that we generally use, and out of them, electromagnetic probes such as photon or dileptons are really popular and unique in their own ways. The main reason is because they are electromagnetic. That means that when they go out as photons or dileptons, they don't interact with the bulk medium because they usually interact only with electromagnetic interaction, and that's why their mean free path is much larger than the average medium size. And that's why, first of all, they carry the more information from the QGP stage, for example, or any other stage where they are emitting from, and because they are not interacting much, so they carry the least contaminated information. Another important aspect of the electromagnetic probes are that they are being emitted from every important stage of the heavy ion collision. So that also takes us to the next slide, because we have electromagnetic probes like photons or dileptons emitting from each of the important stages. How do I identify which stage dominates in for which intermediate mass or which invariant mass? So that's where this plot actually comes in. So both from experimental overviews and from theoretical predictions by a long time ago given by Ralph Rapp, it shows that qualitatively it's similar, and it shows that for low values of the invariant mass, the hadronic decays actually are the dominant process, which gives the photons or dileptons. For very high mass, high invariant mass, the Drellian processes becomes the more dominant one. And for the intermediate invariant mass range, we have the thermal or QGP contributions becoming dominant. So because we are interested in the thermal or QGP contribution in the dileptons, we'll be talking about the intermediate mass dilepton productions. Now, when we talk about the leading order dilepton production, only focusing on the thermal part or QGP phase dileptons, so then the leading or the main dominant process is the quark-antiquark annihilation. And this is the basic structure of the process, as you can see here. So from the bulk medium, a quark and antiquark will interact and give us the virtual photon, which in turn again decay into a lepton and antilepton, which we are calling lepton pair or dileptons. Now, usually when we talk about dilepton production rate, this is a static or snapshot property. That means that when we are calculating this, we are just taking a particular fixed point in the space-time and calculating the rate of this process. But eventually, what we want to do is we want to match our theoretical predictions with the experimental results. To do that, what one needs to do is then take this expression for the dilepton rate and take into the space-time evolution with proper hydrodynamical evolution, and calculate the quantity, which is known as the spectra, dilepton spectra, which is the dynamic property where we have to integrate over the d4x, which is the space-time. Okay, so for the next 2 minutes, I will just talk about the basic formalism of the dilepton rate. So as I mentioned, this is the basic process that we are generally focusing on. So you can see we have an initial phase and a final phase with a lepton and antilepton pair. So if we divide this into if we divide the dilepton multiplicity into 3 parts, which will be emission amplitude, and then we have the thermal weight factor and the phase space factor. And emission amplitude, again, we can give it with the leptonic part and the photonic part, which we are calling leptonic tensor L mu nu and the photonic tensor M mu nu. Pictorially, one can separate out by this blue shaded region as the leptonic part, leptonic contribution, and the red shaded region as the photonic contribution. Now, here you can see we have incorporated the thermal weight as a density matrix inside this second angular bracket here. So now if we play around this photonic tensor a little bit, you can see what we can do is that we can add this rho inverse rho in the right hand side of the nu y, and then just apply the KMS relation, which will give us just the shift in this y0 component. So y0 will become y0 plus I beta, and then just a simple variable transformation will give us back this extra e to the power minus beta q0 factor in the left hand side. And eventually what we will get, also this sum over initial states will be gone because of the completeness relation. And eventually we will see that we can connect this photonic part with the spectral function, which is in turn nothing but the imaginary part of the retarded one loop photon self energy, or the photon polarization tensor. So that's what I have also shown here pictorially. So basically this red shaded part, which is the photonic part, is now can be represented like this, which is the cut part or imaginary part of the one loop photon self energy. So now this formalism that I just mentioned is derived for the static medium. So for the present work, we will study the effect of weak acceleration, but still for the time being, we are only considering modifications in the correlation function C mu mu. So that means when we have this C mu mu, and when we have the whole expression for the rate, the only modification we will have for the acceleration will come from the C mu mu, which will become C mu mu alpha, as you can see in the blue colored text here in the bottom. So now if we turn our attention to the other side of the talk, which is the local acceleration. So around 50 years ago, Unruh gave us this idea about the Unruh effect, that tells us that when you are in an accelerated medium and you are the observer, you detect an apparent thermal radiation, which is basically dependent on the value of the acceleration. So this is the Unruh temperature that usually we talk about. And if we need to test the effect of this kind of Unruh radiation, what is the best place to do that? Obviously, ultra-relativistic heavy ion collision is one of the ideal places to test this kind of effect. So that's why, because we have this accelerated system and we have the large acceleration immediately after the collision, and this can also be shown by this recent very interesting paper by Georgy Prokhorov and collaborators. As you can see from this picture, that they have shown for both, in the left panel it's given for central collision and in the right panel for non-central collision, and they have done it with the modeling using their PHSD Parton hadron string dynamic model. So here you can clearly see that both just after the collision, the effect of acceleration is much larger, but when you go a little bit further in time, then the effect slowly dies away for both central and off-central collisions. So in the present work, since we are interested in QGP phase, we will be a further down in the time. So that's why weak acceleration seems to be a good approximation to take. So we will work in the weak acceleration approximation. So now if we talk about the formalism in an accelerating medium, first we have to talk about the modifications in the Dirac propagator. So for example, the normal density matrix will now change into something extra, that is exponential minus beta h will become exponential minus beta h minus a kz, where kz is the boost along the z direction, in which direction we assume the acceleration. So then, because of this change in the density matrix, we will have a modified KMS relation, and when you solve the KMS relation, you get back the fermionic propagator in terms of the vacuum propagator, and a modified weight factor, which now depends on alpha, where alpha is the proper thermal acceleration a by t. So now these are the identification points that we have, which depends on alpha, and also if you can see, this tau j is now dependent on z, and zj is now dependent on tau, so it's cross connected. And in the weak field approximation also, when we take the weak field approximation, it becomes a simpler expression. So tau j, all these cos alpha, cos j alpha and sin j alpha are now just alpha factors, but still the cross connection remains. And here you can see this hyperbolic structure, which is akin to the world line picture of an accelerated particle. Okay, so now if we talk about the Dirac propagator again, coming back to the modification of the Dirac propagator. So when we include everything and expand this whole propagator in the weakly accelerated system, first of all, before doing that, we have to remember that this is not anymore translationally invariant. So we have to do this Wigner kind of approach, and from XX prime kind of a frame, we have to change the coordinate to capital X and delta X, where capital X is the average of XX prime and delta X is the difference. So for example, when we have the vacuum or thermal propagator, everything will depend on that difference because it's translationally invariant. But now, because of the accelerating identification points, they are cross connected. So we can't do that, and we have to have them dependent on this capital X. So that is clearly visible also in the expansion. As you can see, this AC alpha is basically expanded propagator in a perturbative series of alpha, where alpha is the proper thermal acceleration. So AC0 will give you just the thermal propagator, and then we have this first order correction in alpha, alpha AC1. So AC0 is just dependent on delta X, and then you have this AC1, which is a non-trivial expression dependent on both capital X and delta X. And it also involves derivatives over del del p tau, where we have to take the Matsubara frequency sum over p tau. Okay, so the next step is, after we have the Dirac propagator in presence of a weakly accelerating medium, the next step is to calculate the correlation function, of course, and then of course you have to go order by order. And here we can't do beyond order alpha, because to go to order alpha square, one needs to calculate the propagator also of the order of alpha square, otherwise it's not complete. As you can clearly see from this picture also, where we have evaluated the imaginary part of the correlation function. So in the left hand side, it's the total correlation function, and its imaginary part. In the right hand side, the first term is just the thermal correlation function and its imaginary part when we are cutting it. And then the next two diagrams will give you the first order correction in the acceleration, alpha imaginary part of C1 mu nu. And then if you go beyond, then the order alpha square will have the one term will be both the fermionic lines will have this order alpha correction, and then you have to take two other diagrams where each of the legs will have two order corrections in alpha. Okay, so yeah, not only this, but after this we have to perform the Matsubara frequency sum. We had to take the imaginary value, because the expression of the propagator is non-trivial. This mathematical process was also not very trivial, and fortunately at the end of all this we found a completely analytic expression, as you can see here. So the upper box is basically the thermal contribution, as we already know from multiple texts. So this actually corresponds to the Born dilepton rate, which is just the thermal dilepton rate. And here in the red shaded box with blue text, you can see the contribution coming from the first order correction in the acceleration, which is completely analytic at this point. So here you can see it's dependent on omega plus minus, and this m is basically the medium contribution coming from different Fermi-Dirac distribution function, combinations of that. Now the next step is to plot the result, because we are currently considering only the static medium. So basically the ratio of the dilepton rate will equate to the ratio of the imaginary part of C mu mu, because the other factors just get cancelled away. So when we are taking the ratio here in the y-axis, when you are seeing this dr alpha by dr0, this is nothing but, again, this is imaginary part of the imaginary part of C mu mu alpha by imaginary part of C mu mu 0, which is the thermal part. So here you can see in the intermediate mass range, we can see some enhancement, encouraging enhancement. So in the left panel, we show the results for increasing temperature with a fixed value of alpha, but of course the acceleration is not fixed, because alpha is a by t, so the acceleration is changing, but the proper thermal acceleration is fixed. With increasing value of temperature, we see increasing dilepton production rate. The same trend is also observed for a fixed temperature with increasing value of alpha. So to summarize, I will not go through all this summary section, but the main key point is that we found enhancement, encouraging enhancement, just by the very preliminary calculation in this avenue. Of course, we need to do many further checks and many further outlooks to talk about. For example, here I will talk about one in particular detail, that is when I talked about the static formalism, static medium, that is, maybe we can justify it for the weakly accelerating system, but when we will be talking about a generalized accelerating medium, then we can't take the medium to be static anymore, which we use for the thermal dilepton rate, or for example for a magnetized dilepton rate. So we need to change the formalism of dilepton production rate due to the local acceleration. I will just show you a glimpse of that. So for example, the density matrix that we were playing around in the formalism, and we change the photonic tensor with that density matrix will now change, and we have this extra Lorentz boost will come into play, and then we have to take this into account and change the whole m mu nu, and basically then this whole dilepton rate formula that we generally use except imaginary pi mu mu or c mu mu, that whole thing will also have some contribution from the acceleration. So this is one change, and then of course the natural extension is to go from weakly accelerating medium to arbitrarily accelerating medium, and we also want to incorporate any arbitrary polarization for the outgoing lepton pairs, not just the unpolarized version. And with that, I thank you for your kind attention.
Thank you, Aritra. Are there any questions? May I ask you, Aritra?
Yes.
This extra contribution to the rate is this something that is missing in the data? As far as I understand, the analysis in the intermediate mass range, at least for several collision energies and different systems, seem to be okay with data. Is there a motivation, experimental motivation?
Yes, the motivation, one of the motivation is, of course, is the overestimation. Actually, when we predict match the theoretical predictions with the experimental data, we always underestimate the data. So, of course, that is one of the motivation to find an enhancement in the dilepton production rate.
Okay.
But with that also, this is the linear ordering alpha correction. So this is coming explicitly from the quantum corrections that we are taking from the imaginary part of the self energy. So when we change the formalism part, we can have other non-trivial corrections coming in alpha, and that may change the overall effect. That's also I want to mention here. But of course, the motivation is, as you said, the difference between this experimental findings and theoretical predictions.
All right, thank you. Questions? Okay, if not, thank you very much, Aritra.
Thank you, Alejandro, again.
And now